So, so we start now to talk about motion in 2 and 3 dimensions. How the motion in 2 and 3 dimensions takes place. We already have studied how to treat the motion in 1 dimension. In 1 dimension, the vectors that you imagine you can have are only existing in 1 dimension. In 1 dimension, you take a position. This is the x-axis. The object can only move in one direction. This is a 1 dimension problem. It cannot go far away from the dimension. So he can be here at the position x1 at time t1. He can be here at the position x2 at time t2. So you can imagine that there is a vector, that is this vector, that makes the position of the particle at time t1. So the vector r1 will be the vector with the magnitude x1 in the I direction. While at the time t2, you have another vector. So this is the vector that will make the position of the particle at time t2. So you will write that r2 is the vector that has the magnitude x2 in the I direction. x2 can be positive or negative. If x2 is minus 3, the vector will be, this is the 0, will be minus 1, minus 2, minus 3. So if the vector is the vector r2 equal minus 3I, is 3 meters in the minus I direction, so will be the vector r2. So r2 prime, let's go to call it r2 prime. So this is the vector r1, this is the vector r2, and everything that we have done, you can repeat it in 1 dimension using vectors. What we have done? We have done the displacement vector. The displacement vector is r2 minus r1. So the displacement vector is r at the time t2 minus r at the time t1. We have done the average velocity, and the average velocity is the change in the vector per unit of time. This is the average velocity. So it's r of t2, the vector r at the time t2, minus the vector r at the time t1, divided by delta t. We have done also the v instantaneous. The v instantaneous will be the limit when delta t tends to 0 of delta r divided by delta t. And this we say that is the derivative respect to times, not a function. It's not a function, it's a vector. It's a vector that is changed. It's the derivative respect to time of the vector. So because the vector is the vector r equal xi, this is the vector. This is the structure of your vector. What is the derivative of r respect to t? I doesn't change. The vector I is always pointing out in one direction that is not changing. In some way, you can imagine that there is a star very far in the same direction of I, and I is not rotating respect to the direction of the star. I is making the direction fixed in space. So we define the instantaneous velocity as v equal the derivative of r respect to t. So we define the velocity as the derivative respect to t of x and I. So if we do like this, so b will be written in this way also. V is the derivative of the vector r respect to t, so, but r is x by I, is the derivative of x respect to t in the I direction. This is the vector v, and can be written like this: vx, the component x of the velocity, by I. Find the velocity v as the derivative of r respect to t. And r is the vector xi. What I'm writing exactly is the derivative respect to t of the vector r, of the vector xi. So I'm writing exactly the derivative of x respect to t of the vector I, because the vector I is not changing. If the vector I is changing, I have to add this term x by the derivative of the chain of the vector respect to t. But because the vector I is not changing, this is 0. So, as a conclusion, v is equal the derivative of x respect to t in the I direction. And this is written in the following way. V is Vx I. So Vx is simple, the derivative of x respect to t. So we go now with the acceleration. How we define the acceleration? The acceleration, we define the vector v in one dimension. We define this is the 0, this is the 1, this is the 2 meters per second. So let's say that I have the vector v1, this vector, v1. And let's say that I have the vector v2. The vector v2 will be this one, v2. v2, maybe v1 is 1 meter per second, you see? Is 1 meter per second because it's occupied 1 meter per second in my scale, and maybe v2 is 2 meters per second or 1.2 meters per second. How we define the average acceleration? We define the average acceleration, A average. How we define? Like v2 minus v1 divided by t2 minus t1. Or in other words, the change in the velocity divided by the change in times. Oh, what is the change in the velocity? It's from v2, it's from v1 to v2. The change in the velocity is here. This is the change in the velocity in this picture. Delta v is this vector. Okay, so this is the average velocity. How we will write this in our term? We will write this in our term in the following way. v2, the acceleration will be, the average acceleration will be v2 minus v1 divided by t2 minus t1. So v2 will be v at the time t2, the vector velocity at the time t2, minus the vector velocity at the time t1, divided by t2 minus t1. But the vector velocity at the time t2 is the derivative of x respect to t evaluated at the time t equal t2 in the I direction. And the vector velocity v at the time t1 is the derivative of x respect to t evaluated at the time t equal t1 in the I direction. And if we are talking about the acceleration, we are talking about the derivative of x respect to t at the time t equal t2 minus the derivative of x respect to t at the time this average acceleration, So if I take now the instantaneous velocity, I have to take the limit when t tends to 0 to get the instantaneous velocity. The limit when delta t tends to 0 of delta v divided by delta t is simple the change in the vector velocity per unit of time. So I have defined the A acceleration. And if you see here, the average acceleration is the second derivative of x respect to t. Why? Because it's the slope at time t2 of the velocity minus the slope at time t1 divided by the time. So it's the change in the slope. It's not the slope, it's the change in the slope. So it's the second derivative of the function. Okay, so all these equations that I have written, so now let's go to write clearly the acceleration. The average acceleration, the average vector acceleration will be v2 at time t2 minus v1 at time t1, the change in the velocity divided by delta t. So if I write it in 2 dimensions, it will be v2 in the I direction minus v1 in the I direction. So the magnitude of the vector v2, will have a magnitude v2 and a direction I. v2 can be minus 3, so meaning that it's going to the negative direction of the observer, divided by delta t. So if I make delta t goes to 0, the acceleration will be the change in the vector velocity per unit of time. Okay, this is what we have seen in 1 dimension. So to find the instantaneous acceleration, this is the average of acceleration. So to go from here, you take the limit when delta t tends to 0 of the vector A average. So when you take this limit, you take the limit when delta t tends to 0 of v2x, of course, minus v1x divided by delta t in the I direction. And this limit, this part of here, this is the derivative of v respect to t. So the vector A can be written also like this. A equal the derivative of v respect to t, the derivative of the magnitude of v respect to t by I. Okay? So it's the derivative of vx respect to t in the I direction. This is the derivative of v respect to t. So this is the derivative of vx respect to t in the I direction. So this is the conclusion that A is in this case like this, but this will be a general equation in two or three dimensions.